Hi, my name is Al Clark. Today we're going to be talking about jitter and how it affects performance in digital audio systems. My experience in designing audio gear for a long time is that sometimes designers get caught on this is the problem or that is the problem, as if you solve this one thing, everything is perfect now. So I'm not going to pretend that's true, but jitter is an important component into building a high-performance digital audio system. So I want to talk a little bit about what it is, how it's introduced, where we are initially, and then we'll talk about how you reduce the jitter to a level where it essentially is no longer an issue at all. So what is jitter? Well, I'm going to draw just a giant sine wave again, but of course that could be any kind of signal we want. In a digital system, we'll think about this from an A to D converter point of view, but really it's exactly the same when we're talking about it from a DAC point of view. It's just reciprocal. All the audio is the same. So typically we might have a sample here, another sample up here, another sample here, and so forth. And we expect these to be separated in time precisely. Think of a drummer. We want the drummer to probably be keeping the beat accurately and not being a little early and a little bit late, at least not unintentionally. So the idea is that we're going to be taking a sample right here, right here, right here, and right here, so forth. And this brings up, so let's talk about what jitter is next. So imagine you're a little early. We'll say you're so early that you're here instead at this point. Now I realize that's pretty atrocious jitter, but it's easy to see on my picture. So if I was measuring the value that's supposed to be right here, and I was getting that would be some value x, but instead I measured it early here, I'd get some value y. Well, clearly x and y are different numbers. Hence the axiom that we talk about a lot, and that is the right data at the wrong time is the wrong data. And I didn't invent that phrase, but I'm sure you may have heard it before, but this illustrates it. And I want you to remember that, because that's the whole thing why we care about jitter in a nutshell, is that problem. Now, how big is this problem? Well, it all depends. Because if I'm using a modern converter, I can measure the difference between x and y, maybe with a lot of bits if it's a really good A to D converter. What if there was, if this is a 16-bit converter, let's say, maybe the spot here and here, maybe the resolution is down here, in which case I don't really care so much about the jitter because the number would be the same with or without the jitter. But if I'm dealing with a much better converter, I might have multiple spots that I could actually calculate this at, and those numbers are very different numbers. So the first thing to remember is that the higher the performance of the converter, the more bits of accuracy, if you will, the more jitter becomes important. So if you've got a lot of jitter in a system and you've got a really good converter, you should probably just save your money, because your really good converter might not really be a 21 or 22-bit performing converter. It might be a 16-bit performing converter if there's jitter in your system. The second thing is that the sample rate makes a difference of how fast these are changing, because if there's jitter happening at a fast rate, then I'm going to see it sooner. So what are those numbers? Well, in a 16-bit system running at 44.1, you probably can tolerate 300 picoseconds of jitter before it matters. 300 picoseconds seems like a short time, and in some ways it's a very short time, but in the case of signal processing, it's forever. So if we're talking about state-of-the-art audio today, then the magic number that we need to get to might be a couple picoseconds. Once you're better than that, and some people claim they're better than that, it's kind of moot, because the number is the number. If I always measure it and I get x each time, if that's what I'm trying to measure, then the jitter is not really my problem at all, because it's good enough. And having better performance doesn't make it better, it just makes it the same. So this is kind of our goal, is a number somewhere in that order, and close to that number. in terms of performance of jitter. Now, couple things to think about. How do you get jitter? If I've got an A to D converter, doing something with it, kicking it out with the same clocks in the system, then I just have to make sure that my original oscillator is pretty jitter free. So I've got this clock here. This is my clock, we'll say. And I'm going to kick it out to my A to D converter, let's say. So we'll just draw an A to D converter over here. Signal comes in. And maybe I've got some signal processing in the middle. We'll call it a DSP. And we've got a DAC. And it goes to the same clock. And if this is jitter free and this is jitter free, I do some math, whatever, then our output would be jitter free, no problems. Or more correctly, our jitter is as good as that clock. I can wreck that pretty quickly because if I just kind of wire these things kind of haphazardly, you know, I've got something coming here and connecting over here like this. Well, my clock comes down like this, comes here, hits this thing, bounces back, one comes here, bounces back a little bit, not perfectly, and it's sort of like waves that interfere with rocks. And pretty soon, even if this is really good right here, it's a mess. So the hardware designer has to make sure that they've dealt with that properly. And that's something that isn't particularly difficult to do, but sometimes skipped by people who don't think too much about jitter. Okay, so that's a little bit what jitter is and why we might care. So remember, we're trying to get to 2 picoseconds or thereabouts, we'll say, round numbers. How do we get there? Well, we have a couple possibilities. So the first method that I heard about years ago was you'd basically have your digital content. Maybe it's been recorded off a CD, so we'll just say it's data coming in at some clock. We'll say it's jittery by definition. It's coming in, and we put it into a big memory buffer. So a big chunk of RAM, let's say. Could be on a hard drive, could be just a bunch of RAM. And then we, inside here, and we put all this buffer, all these samples into this memory. This might hold 3-4 seconds worth of data in that space. And we put our perfect clock, or as perfect as we knew how to make, here into it. And it's going to be set at some sample rate. So let's say this is 44.1 because this is the old days. And let's say this is 44.1 because it's coming from a CD. But this isn't really 44.1. Well, let's say for a moment, this one's really 44.101. In other words, it's close, but it's not exactly the same because they're separate clocks and they can't both be exactly the same because they're different. So it comes in here and we're going to start putting samples in the buffer, and we start by loading this buffer up and starting it in the middle. And slowly but surely we're going to, depending on whether the incoming clock is slower or faster, we're going to start sliding this buffer with samples. We're going to carry or borrow a little bit. But coming out here, it's going to come out at this rate. And sooner or later, we're going to buffer until we don't have any more RAM, and then we're screwed. So what people would do is they'd say, oh, well, it's a CD, and at the end of the song, we can reset the pointer and reload the song. It's not a very satisfying method. It certainly doesn't work watching a movie. Most of us don't want to hear 3 seconds of latency with the audio and the video. But in a playback system, it kind of worked in a crude way. I haven't really seen, I mean, people did this, they charged a lot of money for it. Frankly, it was a pretty stupid idea, but that's the best they came up with. It seemed kind of okay in their heads. The next method is called the phase lock loop method. And the phase lock loop method works by, I've got this incoming signal coming in, we're going to call it our clock jittery. I go into what's called a phase comparator, and then I'm going to a low pass filter, and I have what's called a VCO, voltage controlled oscillator, going into the phase comparator. And the idea is that I'm going to adjust this VCO so that it, on the average, is the same frequency as that clock. And if I make this low pass filter slow enough, then this will be essentially the average frequency of that, but it won't be as jittery. And the catch is that when I make this kind of technique, I can get rid of the jitter here, but I introduce jitter with the VCO. Why? Because if I have a clock coming in here, I have to be able to adjust a little bit to make this lock. And that means this oscillator has to be able to change frequencies. And if you can change frequencies, the easier it changes frequencies, the easier it is to be jittery. And so without getting into a lot of detail of how one does this best, the best methods I've seen with this uses what's called a fractional end PLL. And one of the best devices for that was made by Wolfson called the WM8805, now Cirrus Logic. And that got you down to about 50 picoseconds, which is not too. So actually it says, hey, that's a great solution for a CD at 16 bits, but not necessarily so good for some of my higher performing things. And in fact, that's a pretty good way of doing it, certainly better than the first way. Now, how bad is jitter? Well, jitter from a SPDIF signal, AS3 signal, probably 300 picoseconds probably intrinsic by the time it gets into the cable and into your equipment. HDMI, probably worse. A radio link, probably worse again. So jitter attenuating to 50 picoseconds is a step in the right direction, but it's not there. And so it's a simple method of doing it, and it's and certainly one of the techniques that people have used. So the third way that we're going to talk about is the way that we do it at Danville. And it starts with an idea called an asynchronous sample rate converter, which is almost always just talked about with this acronym because it's a big long string and because most of us can't spell asynchronous very repeatedly. So in ASRC, the basic idea, at least as far as I know, or the godfather of ASRC, is a guy named Bob Adams. He's a fellow at Analog Devices, and he did this in the early 1990s. And you can find IEEE and AES papers to this effect on the web. And so what is this ASRC thing? And we're going to talk a little bit about that and how it can help us. The primary idea of an ASRC was to convert sample rates from one sample rate to another. Now, in general, if you want to go from, say, 44.1 to, I don't know, let's say 48, and you control everything, or it's just a digital stream, you don't need an asample synchronous converter in ASRC. Why? Because that ratio is called is rational. It's 147 to 160. Now, that seems like a hard ratio to do, but in essence what you're doing is you're going to interpolate and decimate by 147 and 160 to get this ratio, and you can do that because that's what the ratio of 48 divided by 44.1 is. And you use something called a polyphase filter. And that seems complicated, but trust me, that's not particularly complicated. Just know how to do it, and it's rational. That's usually just called an SRC without the A. And it has nothing to do with jitter. So I wanted to give this only for context. So an asynchronous sample rate converter, so instead of going from 44.1, let's say, to 48, let's say because our clocks come from different places, maybe this came from the CD player outside, and this comes from a local clock. So let's just say this is 48.001, the local clock. So that ratio is no longer, you know, that 147, 160 kind of thing. Now it's an ugly ratio. And that's what an ASRC addressed. So how does this all work? Well, it works something like this. Imagine that if I want to interpolate up, what I do basically is I have a signal that looks like this. Here's the other sample rate, so forth up here. And I basically interpolate by filling, first I do something called zero padding. We're not going to worry too much what that means. And then low pass filtering. What effectively I do is I create a whole bunch of new samples that fill in the gaps at a high rate. And if I know that ratio perfectly, I also know where to tap them off. Now, if you actually did that and created all those filters, you'd only have to have millions and millions of different filters to do all this, which I'm pretty sure we wouldn't want to have. Or you're effectively interpolating first into the gigahertz region, or probably higher, and then decimating down to audios. That's not going to happen. So So the idea was, well, and you have to use what's called a polyphase filter, and all those there's lots of different ones. So they calculated the polyphase filter on the fly, and it's clever. The second thing you need to do is you need to know what that ratio is. So remember I had, let's say 48,001 and 44.1. If I wanted to calculate that ratio with lots and lots of precision, I don't want to do it by measuring one cycle to one cycle. I can't measure that accurately enough. But if I look over a long time, I can calculate that ratio pretty accurately. And that's what a good, well-crafted ASRC does, is it measures that ratio over maybe a few seconds. And if it knows that ratio, it knows how to pick that virtual filter. Now, how does that apply to jitter? Well, let's go back to a sample rate. We'll just say, it doesn't matter whether they're dissimilar sample rates or the same, but we'll just pick it the same because it maybe is conceptually kind of. So we'll just say this was our magic set of numbers, 44.1 and 44.101. So what it does is it comes in, so that's the ratio that we're going to calculate. We're going to pick this filter, and here's what happens from a jitter attenuation point of view. I've got incoming signal coming in, which is jittery. And as long as we haven't dropped any bits, in other words, it's not so jittery that the data isn't being acquired properly, which is pretty safe to say is true, comes in the ASRC. And the ASRC, no matter how jittery this is, for the most part, it's going to compare it to this clock here, which is my local clock. And if I've done a really good job with the local clock, meaning it doesn't have jitter, its jitter, let's say, is my 2 picoseconds or thereabouts, then the jitter of the signal coming out will be as good as that clock. And that means that I can start with something horrible, 300 picoseconds, let's say, or 500 picoseconds, or 50 if I had my PLL that we talked about earlier. But what comes out of the ASRC, if this is great, is essentially as good as that. And that's the trick. So what we really do is we take this clock, we make sure it's applied really well right at the DAC, or for making measurements coming in, really good right at the A to D, and everything else just works out because that ratio that we just calculated is going to be the same whether it's jitter or not. And so that's the basic idea of ASRC jitter attenuation. But I do invite you to read one more thing, and that is there's an article or a tutorial by someone who used the handle Werewolf on do-it-yourself audio. It was done in about 2004, and it was done by a guy who was one of the principals of Silicon Labs. And it's probably the best tutorial I've seen on ASRCs. And so I'd invite you to read that because he explains this in far, far more detail than I have today. And I think you get a much better appreciation of how it works. So thank you for taking the time to listen to this presentation, and we'll talk to you next time.